Alrighty, howdy everyone. Welcome to your review session. I'm assuming everyone here is from Dr. Altman's class. Yeah, sweet. I'm assuming we want to do test review stuff.
Yeah.
Cool. Okay. Where would we like to begin? Does anyone have any specific questions on stuff we want to cover? Yeah.
When determining the less Lewis structure for
Mhm.
a molecule,
Mhm.
is it the what formal charge just at the central atom to be zero?
No, so it's going to be the formal charge of all of your atoms
Be zero.
to be zero. So, I think on the exam, or at least on a mock exam, that you were given, you had OCl2. And you wanted to find the best Lewis structure for this compound. So, do you remember, do you recognize this question? Yes, okay. Right, so the option that is correct is this Lewis structure here. So you have 3 lone pairs on each of your chlorine atoms, then 2 lone pairs on your oxygens. So if we found the formal charge of chlorine, what is the formal charge formula? Mm-hmm. Perfect. So I like to write lone pairs as non-bonding electrons. Right, so you have your bonding electrons is 1/2, and then your non-bonding is going to be the lone pairs. So this turns into dots minus your lines. Those work out to be the same. So how many dots or non-bonding electrons does chlorine have? Has 6. How many bonding electrons does it have? Has 2, so we take 1/2 is 1. How many lines does it have? 1, right? So we see how those two line up. So it'll be 1/2 of 2, which is 1. And then how many valence electrons does chlorine usually have? Good, it has 7. So in this case, your formal charge of chlorine is going to be equal to 0. The chlorine on the left and the chlorine on the right are exactly the same. So both of your formal charges here will be equal to 0. And then if we solve for oxygen, you also get a formal charge of 0 for oxygen. And you can prove that to yourself for a little bit extra practice. So in this case, this is going to be the best Lewis structure for OCl2 that we drew first, because all of your formal charges are minimized, as in none of them have a charge if they don't have to be. Sometimes people throw in like a double bond here or something, and that would create a formal charge where one might be -1, one might be +1. And in that case, this all compounds or all elements 0 is the better choice. Yes. Say that again.
Will the formal charge always be 0 if like the elements?
Satisfied. So not necessarily. So oxygen, when it has a double bond in lone pairs, as in, right, it has 2 lines and 4 dots. This is when formal charge is equal to 0. Octet rule is satisfied. But oxygen could have a case where it has 1 single bond and then 3 lone pairs or 6 dots. In this case, oxygen has a formal charge of -1, but the octet rule is still satisfied. So you do have to calculate it in order to determine what the formal charge actually is. Great question. Anything else on Lewis structures or formal charges? Does this make, yeah. For like how we would solve for it? Yes, yep. So for the formal charge of oxygen, how many valence electrons does oxygen usually have? It has 8 when it's satisfied. What is it from the periodic table? 6, yep. So we have 6 valence electrons that it usually has. How many non-bonding electrons does it have? Has 4, right? There's 4 dots. How many bonding electrons does it have? It has 4 total, right? Because we have 2 from the single bond on the left and 2 from the single bond on the right. So we take 1/2 of that, it's going to be 2. So formal charge of oxygen is 6 - 4 - 2, which is 0. And that's how we got the 0 for that one. And then you can solve that again for the oxygen with the -1 charge. You can prove to yourself that it's -1. What other questions? Yep.
Can you go over the relationship pressure?
Absolutely. So when we talk about vapor pressure, boiling point, and molar mass, what's one thing that ties all 3 of these concepts together? IMFs, right? These are going to be what determines the boiling point, and the vapor pressure and how that relates to molar mass. So if we have something that has a high molar mass, are we increasing our IMFs or are we decreasing our IMFs? We're increasing. So the higher the molar mass, the greater the IMFs. We can look at this in terms of your halogens. So if you have fluorine gas, chlorine gas, bromine gas, and iodine gas, or sorry, bromine liquid, and then iodine solid, right? These 2 are gaseous. This is a liquid and this is a solid. The only thing that is, or I guess before I ask that, what is the intermolecular force between your fluorines, your chlorines, your bromines? London dispersion forces, right? So these only have dispersion forces. Okay, so the only thing that's changing as we go down the periodic table here is how big our elements are. So iodine is much, much bigger than fluorine. And because we have so many more electrons within our system here, we actually create so much IMF intermolecular forces here that cause it to be solid, right? Our IMFs become so strong, they tighten our two elements together and they form a solid. So in this case, right, as molar mass increases, your IMFs increase, which therefore make your compound less gas-like, right? Makes it more liquid or makes it more solid even. So if something is solid, what does that mean for its vapor pressure? Is it going to have a high vapor pressure or a low vapor pressure? It'll have a low vapor pressure. So as we increase molar mass, we said we're increasing IMFs, which means we're decreasing our vapor pressure, right? Because we have less ability to reach the gaseous phase, right? In order for iodine to create a gas, it has to go through its liquid form first and through its gas, and then escape to its gaseous form, right? It could sublime and go directly to your gaseous state, but that requires a certain pressure and temperature, right? So the greater the IMFs, which is from higher molar mass, decreases your vapor pressure. So then if vapor pressure is low, does that mean we're going to have a high or low boiling point? We're going to have a high boiling point, right? In order to get iodine to the gaseous phase, we have to increase its temperature a lot. So that means that in order for it to boil, in order to reach the gaseous phase, we need to put a lot of heat into it. So if we have a low vapor pressure, we have a high boiling point. And that all stems from the intermolecular forces that are happening within our compound. Does that help answer your question? All right, so something has, right, if they're all about, let's say within like 30 grams per mole of each of your compounds, and we have compound A, I guess we'll do this. Alrighty, so we have 3 different compounds, each with their molecular weights. And for your IMFs, compound A only has London dispersion forces. Compound B only has dipole-dipole, or I guess the highest one it has is dipole-dipole. And compound C, the highest is hydrogen bonding. Which one's going to have the highest boiling point here? C, compound C is for 2 reasons, right? We have the highest molar mass, and we also have the greatest intermolecular forces. So this compound C is going to have the highest boiling point. What does that mean about its vapor pressure? It'll have the lowest vapor pressure. That makes sense in terms of an example. Any other questions on that topic? Okay, what other questions do we have?
What's the difference between like dipole-dipole dispersion forces, dipole-induced dipole, and induced dipole-induced dipole?
Good. So whenever we have the word induced dipole, that means that we have 2 separate compounds. So we could have something where we have an ion-induced dipole, and this means that we could take fluorine, which is usually just regular old dispersion forces, non-polar. If we bring in a sodium ion, is that positive or negative? Or is the sodium ion positive or negative? It's positive. What charge our electrons? Negative. So which way is our dipole, or where is our electrons going to be attracted to? Towards the center, in between our two elements, or away from that? It'll be towards, right? So if we now have our electrons on this side, which way is our dipole going? Towards the sodium ion, right? So in this case, we induce a dipole towards the left because we brought in a positive charge. If we instead brought in a negative charge, which way does our dipole go? It goes the other way, right? It's going to go towards the right, or I guess towards the right this way. Right, so that's inducing a dipole. You bring something in with a charge or something with a dipole itself closer to a nonpolar object, and therefore it creates a dipole within your otherwise nonpolar substance. The same thing happens for dipole-induced dipole. That would be like bringing a carbon-oxygen bond. I guess that. Right, so we have carbon oxygen. This is going to have a dipole like this. So if we bring fluorine in here, we now have the negative charge hanging out towards the right-hand side of our compound here, right? This is where our negative charge is hanging out. So if this is where our negative charge is going to be repulsed in the fluorine compound, creating a dipole in the same direction. And then if you take it away, right, if you remove this, this also gets removed and you return back to your nonpolar substance. Yes.
The homework, issues raised.
Yep.
Why wasn't there, well, in the homework itself, there wasn't any hydrogen.
Great question. So right, we have this aldehyde here. We said that our dipole, right, we have a dipole that goes like this. What are the requirements for having a hydrogen bond? Good, it has to be N, O, or F directly bonded to a hydrogen. So that means you need to have N bonded directly to an H, O bonded to an H, or F bonded to an H. In this case, what is oxygen bound to? It's bound to carbon. So if you have just a big slurry of this HCOH compound, it cannot hydrogen bond with itself because there's no oxygen-hydrogen bond directly. If you dissolved this aldehyde in water, that could bond, or that could hydrogen bond with water, because water's the thing that has the hydrogen bond, and you do have a dipole here that can bind with that. But just within the pure substance of this HCHO compound, there is no hydrogen bonding. Do you see why that's the case? So you need to have an HOH like sandwich here. So no matter what we do, we can't rearrange that compound up top in order to create an HOH sandwich. So that's why I can't hydrogen bond with this. But water, on the other hand, right, we can have this structure here, and then another water molecule can come in, and then we have the HOH bond that we're talking about. What other questions? Yeah.
Can you show us like this,
Like the radii, or
well, no, I saw some of like, gotta find like this.
like how between like a single double or triple bond? Yes, yep. So I think you have a mock exam question like that. Maybe not. I thought you did, but in any case. All right, you can have carbon, carbon, carbon. All right, so you can have these 4 bonds here. In terms of bond length, which one is your shortest, your triple or your single bond? Your triple is your shortest, right? So we go bond length, short to long. Your triples here, your doubles here, your singles here. So in this case, the general length of your single bond is all the same. But what changes between these 4 compounds? The electronegativity, the strength, right? All of these are going to change. When we compare just this right column here, which way does the periodic table go? We have carbon, then what follows it? Nitrogen, oxygen, fluorine. What's the trend for size as we go across the periodic table? Bigger as you go to the left. Yes, right. So electronegativity is going to increase as you go across. If it's increasing in size to the left, that means it's decreasing to the right. So if carbon is bound to fluorine, we have a basketball bound to a ping pong ball, right? So those can get pretty closer in terms of the center of their radii if we compare carbon as a basketball to carbon as another basketball, right? We can say that this is a basketball. We could say this is a softball. This is a baseball. And this is a golf ball. Right, so those are the relative sizes of all of them. So the basketball and the golf ball can get a lot closer together than the basketball and the softball can. So in terms of length, which one's going to be the shortest, your carbon-carbon bond or your carbon-fluorine bond? Your carbon-fluorine bond is going to be the same, or is going to be the shortest, because they can get the closest together in terms of their radii. Does that help with that? Right, and then you could also look at it between 2 different compounds. So if you have a carbon double bonded carbon and then an oxygen double bonded oxygen, which one's going to be your shorter double bond? Your oxygens, right? They're inherently smaller so they can get closer together, and therefore your double bond between them is going to be shorter than the carbon-carbon bond. Does that help with that?
What's the like trend, I guess you could say, for like the electronegativities and their relations, like polar, covalent?
So your periodic table, these are going to be your metals. These are going to be your nonmetals. And these are your transition. If you have metal, nonmetal, this is going to be ionic. If you have nonmetal plus nonmetal, this is going to be covalent. If you have nonmetal A and nonmetal A, this is nonpolar because they're the same nonmetal. And if you have nonmetal B plus nonmetal A, this will be polar because they are different compounds and will have different electronegativities.
Yeah, the trend with like, I guess the given value, isn't it like 0 to 0.5? That's 0.5 to 1.5 and
Yep.
5 to 2, and then it's what? ionic, ion, covalent, covalent, you know?
Yep, so it should be like 0 to 0 point, I think it's 0.5. This is non-polar. 0.5 to 1.5 is gonna be polar. And then greater than 1.5, it might be 1.9, something like that. This will be really polar. Or not really polar, it'll be ionic. I think it might be 1.9. Don't quote me on that. Check your notes real quick. But if you have non-metal, so such as carbon, oxygen, those are two separate elements that will be polar. The only time you're going to see two different elements that is still non-polar, it's going to be hydrogen and carbon.
This is like O2 or something.
Mhm.
Keep it as 0.3.
Yes, so if you have, you're saying O2, right, and then oxygen is 2.3 electronegativity. Yep, so that's just saying that oxygen double bonded to oxygen, you have 2.3 here, you have 2.3 here. There's no difference in electronegativity, you have a nonpolar compound. Noble gases you can pretty much just ignore. What else?
Does dipole forces only have?
Yes, yep. So in order to have a dipole-dipole interaction, you have to have an established dipole already. So that would be like carbon, nitrogen. Those are going to be different elements. They'll have different electronegativities. You'll have a dipole like this, so they can dipole-dipole interact with other CN molecules. Yep. Great question. Yep.
What exceptions are these? Hybridization. Like copper as an exception, but like when you're right.
Yes. Yep. So when you're filling your SPDF notation, your electron configuration, instead of having it starts in period 4. Instead of having 4s2 3d4, you'll actually have 4s1 3d5. And same thing, instead of having 4s2 3d9, you have 4s1 3d10. So I believe this is chromium is your first example and copper is your first example here. So anything in those rows underneath chromium and copper will follow the same trend. So even molybdenum is under chromium in period 5. That would be 5s1 3d4 or 3d5. Sorry, 4d5. So the energy levels at these two places, your 4s has this energy level and your 3d is slightly higher. So it's actually better to have instead of having 4 orbitals that are unpaired with one that is paired, it's actually more energy favorable to have all of your orbitals in the highest portion. It's actually more energy favorable to have all of your orbitals with one unbound electron. So that would be the case for chromium, right? This is more, instead of having, right, 4 people that live on their own in one empty room and 2 people sharing a room, everyone gets their own space, right? And then in the case for copper, right, you have one orbital that has one non-bonding electron. So it actually reduces the energy to take this bound one and bring it up here instead. So it's an energy saving technique.
That only happens in the d orbital.
Yep, for your case, that only happens in the d orbital. And then, right, kind of going along these exceptions, right, remember that as we're filling up your electron configurations, if we look at period 3, we have sodium, magnesium, aluminum. Right, this is going to be 3s1, 3s2, 3s2, 3p, 3s2, 3p2. Right, and starts your electron configurations like this. Your ionization energy, or the ability to remove your electron from each of your respective elements, right? Na, sodium, only has one unbound electron, so it's gonna be pretty easy to take off that electron. But when we add 2 to it, magnesium is gonna be a little bit harder to get rid of that bound electron now. We actually see a reduction in your ionization energy for the 3p1 electron of aluminum, because that's unbound by itself in a higher energy level. So aluminum actually wants to get rid of that electron a little bit more easily than magnesium wants to give up its electron, even though it's a third electron. Does that make sense? Right. This has 1, this has 2. This has a higher energy non-bound electron that it can easily get rid of. So your ionization energy would be 5, 10, and this is actually 8. Yep. Mhm. So which of the following atoms is paramagnetic? This one?
Yes.
Yep. So what does it mean to be paramagnetic? We have lone electrons. Good. Right, so we want unbound electrons. So what is how many unbound electrons does sodium have? Has 1. What is, and this is 3s1. What is radon? Does anyone know? It's element 120, element 86. It's actually a noble gas. So do noble gases have any unpaired electrons? No. So this is noble gas. Right, that's all paired electrons. Where is barium? Yep, so this is 6s2, which has paired electrons. Sorry, paired electrons. And then what about mercury? Close. It is a transition metal, but we're in the 6th period now, so it's going to be 5d10. But still all paired electrons. So which is the only one that doesn't have a paired electron? Sodium. So sodium is going to be your paramagnetic element.
So it's paramagnetic as simple as odd coefficient in the last, I guess, orbital.
Yeah, pretty much. If we look at like carbon, This is 2s2, 2p2. This one is paramagnetic because our p orbital has two unpaired electrons. Okay, so you have to just, it's not totally odd because this one, there's unpaired electrons and that's two, and it's still paramagnetic. Even oxygen is 2s2, 2p4. This has one paired electron, but there's still two unpaired. It's still paramagnetic.
That's because there's, three, orbitals.
Yes. Yep. Right, and even with like Mercury in 5d10, right, if your d orbital electrons are non-paired, then they would also count to be paramagnetic. And there's 5 chances to be unpaired there.
Does it fill the orbital going like for oxygen?
Mhm.
Like the first box has an up arrow, the second box has an up arrow, the third box has an up arrow, and the fourth box has a down arrow?
Yeah, by convention, you do the up arrow first.
Okay. So, like 2p5, would that be paramagnetic?
It-
The orbital-
Yep, right, so fluorine. Right, still has one non-bound electron. So oxygen is more paramagnetic than fluorine, but fluorine is still paramagnetic. Yes,
I had seen a rule where it was like all like elements with odd electrons are 10, excluding 10, 16, 32 were paramagnetic, and then every other number is diamagnetic. So that generally true.
I believe that's generally true. Right, for your, I think you said 10, 8, 10.
16, 18.
Yep. Because 10 would be like your full shell. And so that's why it wouldn't be. But other than that, paramagnetic. Yep. Yes, absolutely. Okay, great question. So question 5, we have consider the de Broglie wavelength in a ping pong ball, and the de Broglie wavelength of a baseball moving the same speed. Which of the following statements is true? So what is the equation for the de Broglie wavelength?
H over M2 for MV.
Perfect. Right, and what of our units here? What are your components? What is H? This is constant. This is Planck's constant. What is M? Your mass. And what is V here? This is velocity, right? So this is your speed. So if we compare our ping pong ball of 0.003 kilograms and our baseball of 0.218 kilograms, which one, or what's the only thing that's different within our equation between those two? The mass is, right? So okay, so those are the same otherwise. So if we have a smaller denominator, what happens to our wavelength? We get a longer wavelength, right? It gets bigger. Our wavelengths gets bigger. So smaller mass, oops, is equal to a bigger wavelength. So will the de Broglie wavelengths be the same? Nope. Which one should have the bigger wavelength, the ping pong ball or the baseball? The ping pong ball should have the larger wavelength, right? The smaller mass is the ping pong ball. So this equals the larger wavelength. So the de Broglie wavelength of the baseball is longer than the de Broglie wavelength of the ping pong ball. Nope, that's not it, because we just said the ping pong ball has the bigger one. And then the de Broglie wavelength of the ping pong ball is longer than the de Broglie wavelength of the baseball. We said that's true. We just proved that. The de Broglie wavelength of both are longer than the de Broglie wavelength of an electron moving at the same speed. No, right? Is an electron smaller or bigger than a ping pong ball? It's smaller, right? It has an exponent times 10 to the negative 19. That's the charge, negative 34. So if that negative 34 is in the denominator, that means we're gonna have a really, really big de Broglie wavelength. So that would actually be the longest wavelength. This one is also incorrect. So C is your correct choice here. Yes.
I know you're not actually solving for wavelength, but like if you were to, and you change mass to grams, like
For the de Broglie wavelength, you keep it in kilograms. Yep. Yep.
What are the points in the phase diagram?
Yes. So what is A? What do we call that? This is going to be your triple point. And so what is present at the triple point? All three phases, right? What phases, where are the phases on our diagram? What's this section here? This is solid. What's this one? Liquid. And this leaves this one as the gas. I like to think about your phase diagrams as in terms of like which is more dense, is that the heavier or the more denser object is going to be leaning on the next substance. So here the solid is leaning on the liquid because it's more dense, and so your slope is leaning towards the liquid. Your liquid is more dense than your gas, so it's leaning onto your gas. If your liquid is more dense than your solid, then it'll be leaning this way onto your solid. And so that way you can remember the two and which one is more dense or less dense. Alrighty, so if we're on this CA line here, what does that represent? Or if I guess we're on any of the lines, what does that represent?
The difference between solid and gas.
Yep, and so what do we call that? I guess if we're,
Sublimation.
that's sublimation. And so what is sublimation an example of?
Dry ice to carbon dioxide.
Yep, so that's one of them. I guess what category does sublimation fall under? What if I told you evaporation? What does that fall? What is that called? What type of thing is that? Maybe my question's poor. Right, these are all, any lines are phase changes. That's what I was trying to. Right, we're changing from solid to liquid or liquid to gas or vice versa. Yep, so if you go the other way, if you go from gas to solid, this would be deposition. If we're on the line segment AD, what are the phase changes happening there? We go from solid to liquid, what is that called? That's melting. What about the other way? Freezing. What about line segment AB? We go from liquid to gas. Boiling or evaporating, either one. And what about gas to liquid? Condensation. Right, so those are all happening across those lines. So it doesn't matter on any point along that AB line segment, you'll have melting and condensating at any point along that line. Right, both phases will be present. And then what do we call B? What is that point called? Yep, this is your critical point. Not super important, but if you need to label it, that's what that one is called.
What is that like?
So any temperature or pressure above the critical point, then your phase will have liquid and gaseous properties. You can't distinguish between liquid and gas.
That's the end of the phase change.
Yeah. Yep, any time above that, it's just mush. Yep.
That one.
No, it's just, you just need to know that that's where the critical point is. Does that help? Whoever asked that. D is just saying that that's going to be a phase change. So D here it's on the line segment for your melting and freezing. Yep, so that's just indicating a phase change.
C to A, is that something? Is
So the C to A, if you went from C to A, you would just be phase changing the whole time. Yep, you would have to cross, like how I drew the arrows, you cross, that's gonna be your actual phase change. So the segment corresponding to boiling would be right A to B for this question. Because you want that whole line segment here. Yes, yep, so, right, even if there's two ways that this question could be asked. You could say the phase diagram below segment A, B corresponds to the boiling point, or it could say the condensating point. Right, if you asked either one of those, A, B would be the correct answer here. Does that make sense? Okay. You don't have to go from A to B, you have to cross that line in order to do the phase change. Nope, so that's still, even with water. Right, this is still your freezing and melting phase change. You're just getting more dense as you cross it. What other questions? Alrighty, so number 11, the equally sized, sorry, 3 equally sized beach balls are filled with N2, O2, and F2 gases. The pressure in each of the balls is equal. The balls are stored in the same room over a long period of time. The gases will effuse out of the balls. What of the following statements is true? So what equation are we looking at here? Rate of effusion. Yep. So we have rate is equal to you could do single rate, you could also do rate over rate, whichever one you know. So what's the double rate one? Good. So you can look at it this way, where rate 1 over rate 2 is equal to the square root. This is a whole square root. Yeah. So I believe rate is 3 RT over mass. Single rate looks like this. So when you put rate over rate, the 3 RTs cancel out, and that's why you end up with the inverses of the molar masses. Right, but the point here is to look at your single rate, because your R is a constant, and so that's gonna stay the same. And all of the beach balls are stored in the same room, which means they're all stored at the same temperature. So 3 RT becomes a constant. So the only thing that's changing between the N2, O2, and F2 beach ball is the gas that's present within the beach ball. What does this rate equation tell us? If it's faster, is it gonna if it's smaller, is it going to effuse faster or slower? It'll effuse faster. So the smaller the molar mass, the greater the effusion. So which one, N2, O2, or F2 is the smallest? N2 is your smallest. So what should effuse what should deflate the fastest? N2 should deflate fastest. Okay. Now we can look at all of our answer choices. So choice A, the nitrogen filled ball will deflate more quickly than the other balls. That's negative, right? We said that N2 should diffuse. I'm sorry. Will deflate more quickly. Yes, we liked that one because that one should be the fastest. The 3 balls will deflate at the same rate. Nope, we said they will right? This is dependent on the molar mass. They're not all the same molar mass. They will effuse differently. The three balls have the same masses. Nope, right? Different compounds, gonna weigh differently. And then the fluorine-filled ball will deflate more quickly than the other balls. We said no, because the bigger the molecule, the slower it will effuse. So that's why this one is incorrect, and A is your answer choice.
Did the rate equals square root of 3RT over molar mass unit?
I believe this is given to you as a single rate. If not, it's in your notes, and that's where I pulled it from. But the rate 1 over rate 2 is like
Yeah.
where that derives from.
Okay, how do we like, I guess, derive that?
Mhm. So we have rate 1 is equal to 3RT over molar mass 1. We're going to divide that by rate 2 over 3RT over molar mass 2. Your rates stay the same, so this still stays as rate 1 over rate 2. But now you can put your 3RTs over molar masses under the same square root. So you get 3RT over molar mass 1 divided by 3RT over molar mass 2. And then keep change flip. Yep. So these will cancel out, and you end up with the square root of molar mass 2 over molar mass 1. Yes. Yep. So for R, you have 0.08206 liters per ATM over mole Kelvin. And then R is also equal to 8.314 joules over mole Kelvin. This smaller R is for your gases. Gases take up space, right, a volume, and they exert a pressure. So that's where your ATM comes into play. Your joules is an energy. So this is all of your energy components. So this is when we talk about light. So gases for small r, light for big R. Big R could be right. So these are the three like light equations we usually use. So big E here is that energy, and that's where that comes into play. It doesn't exactly involve R directly, but you would use that energy to solve for R someplace else. And so that involves like transitions between I lost my words. These guys. Right, if you're finding the transition, the energy transition between this one, the constant out front involves an R, that's where that would be from. I don't think there's any practice with big R on your mock exam. Yeah. Big R will come into play when you start talking about thermodynamics. So. Yep. Mm-hmm. Good. So which transition results in the emission of the photon with the longest wavelength according to the energy diagram below? So two things that are highlighted importantly for you is emission. If we're emitting, are we going from low to high or high to low? We're going from high to low. Right, in order to go from 1 to 3, we need to absorb energy because they're higher energy levels. So absorbing goes from low to high, but if we're emitting, we're falling back down. So that's going to be a high energy level to a low energy level. If we're talking about a long wavelength, does that mean high energy or low energy? Higher the wavelength, lower the energy. All right, so if we're looking for the longest wavelength, are we looking for a small energy transition or a large energy transition? We're looking for a short one. So which one's going to be the shortest?
3 to 2.
3 to 2. Yep. Right, and you have 3 options for emission here. You can have 3 to 2, 3 to 1, or 2 to 1. Okay. They should be spaced where it like is scalable. So the transition between 3 to 2 is the smallest transition. That will be the smallest change in energy, which means the longest wavelength emitted. Does that help your question? Yep, great. What else? Do you feel better? Yeah? Yep.
Zero base is something like polarity, like the structure specifically.
Yes. Like overall dipoles and stuff, or, yep. So the big thing to look at for like molecule polarity, you first want to look for lone pairs. Like 75% of the time, if it has a lone pair, it's going to be polar on the central atom, or I say lone pairs on central atom. That might be closer to like 80%. 80% of the time, if it has lone pairs on the central atom, it's going to be polar. And then you want to look for symmetry. Yep. If the electron domain geometry, yes, yes, because we could have an electron domain of 6, and what is that shape? This is octahedral. Or we can have an electron domain geometry, and then we have a molecular geometry of 4. What is this shape? Sorry, if you have an electron domain geometry of 6, but your molecular geometry is 4, it would be square planar. So right, in this case, are there lone pairs on the central atom?
Yes.
Yes, but is there symmetry within our compound? There's also yes. So in this case, your lone pairs are opposite each other. They're in the axial positions. And so the lone pairs cancel each other out. Like their dipole cancel each other out. So this is overall a nonpolar molecule. Do you see why that's the case? Right, that would be like my phone is the xenon and then the fluorines at the corners. You have a lone pair up here and a lone pair down here. So because you have 2 lone pairs, they're going to cancel out. Overall making it not polar. Yes. So, right, so water is a great example of that. What is the electron domain geometry? Tetrahedral. So now we have the tripod and then something on top. I've now taken these 2 guys away, right? So now I just have these 2 on top. My polar bonds, right? I have 2 lone pairs within the tetrahedral position still. So those don't have anything canceling it out because I have 1 bond pulling this way and I have 1 bond pulling this way. So those do not cancel out because there's not symmetry because they're going to push your bond angles closer together. Yeah, it could be. Or like that. It's just the way you draw it. It is, right, it's a 3-dimensional shape, so it's just rotating, right? Between that guy and that guy, it's really just rotating. if whether you're looking at it so that the lone pair is coming out of the plane or going into the page.
Well, no, I mean, like, is there a reason that it can like propel the, like, hydrants to make it symmetrical?
Yes, yep, sorry, good question. Your lone pairs are gonna take up more space, so they'll push the, they'll push the bonds of the hydrogens closer together, but those hydrogens will still have electrons, right? Those bonds still have electrons, and so there's no way that they can push it so that it's like linear, right? Because then your lone pairs would be opposite each other and your bonds would be opposite each other, but then that creates a 90-degree angle between the lone pair and the bond, and that's going to be too much repulsion, where if it was like 109 or 104 degrees away from each other. Yes, they won't be in the same plane. Yep.
The bond angle for that's less than 120 degrees, right?
Close. This one's less than 109 because your tetrahedral is 109. If you had, I'm just gonna use X's and Y's. In this case, it's less than 120 because you have the triangle first. Yep. Just think of a right? Think of your triangle within your square or within your circle, right? These are all 120, 120, 120. Yep. What did I want to draw? That's what I want to draw. Right? Those are all 120 for yours. No, it's good. Anything else?
Remember all the geometry?
An acronym I have not come up with. But I truly believe they look like what they're actually named. If you remember the electron domain geometry, then you can kind of start picking off different positions, and I promise you it looks like what they're named after. If we look at octahedral, for example, I need more space. So if you look at octahedral, you have your Y's on the like up and down, those are going to be straight up and down. So if you removed this guy here, you now create a square bottom and then a point on top. This is called square pyramidal because you have a square bottom with a pyramid where they all converge. So I guess I don't use an acronym, I think of real life examples. So I think of this one as the pyramids of Egypt, right? You have your Egypt pyramid here. And then if we remove another one, this is now square planar because they can all lay flat in a square on the plane, right? You could just, right here, you can move your compound around and it looks square planar. So I literally just think of a piece of paper for this one. And that's how I remember that one. Right, seesaw looks like a seesaw if you orient it correctly. Your T shape looks like a T within the two and the axial and the one coming off equatorial, and then bents, all of bents. Tetrahedral, I always say, is a tripod with a camera on it. So, and then what is that? Trigonal pyramidal is the tetrahedral without the camera on it. So it's just a tripod. It converges to a pyramid with this with the triangle base. So if you can kind of think of like real life examples, I think that might help you memorize them all.
Do the axial like bonds go away first?
Depends on the electron domain. So for 6, yes. For 5, no, it's the equatorial. I guess, so. Yeah, if you go 5, 6, right, that goes in numerical order, so. Then it goes in reverse alphabetical order for which one comes off first.
That's lots around my mind.
If you,
I have a good understanding of, you know. like-
yeah, if you can visualize the shapes, I think that helps you pick which one is gonna be picked off first. Or if you memorize that square planar comes off axial, because it ends up in a plane, then you know that the electron domain of 5 is just opposite. Anything else? Okay, well, it is 6:35, so we can wrap it up there then. Want to go over this again, I will. This has been recording, so I'll post it later tonight underneath the office hours page. For your viewing pleasure before your exam. What's that?
Is that only 5?
Yes, yep. Good luck. You're gonna, I think it's 15 or 16. I think there's 11 or 12 multiple choice and then 4 short answer.
The exam?
Yeah. Yeah, I think yours was 15 and I think Dr. Altman's is 16. Just because they have like 10 extra minutes. or so.
On the rate of diffusion.
Yeah.
When it's like rate equals square root of R, 3 RT over molar mass, R is rate. Or
R-
is that big R?
That is big R.
Okay, okay, and then T is time?
Yes.
Okay.
RT
gotcha.
is temperature.
Temperature, got it,
Yep.
thank you.
Yep.
Dr. Altman was bad with that last.
I don't remember what the last question was.
The exam, like actually, they're all alternate rates, I can talk about.